Related? Yeah. So, if we look here, enthalpy is, if we look at the Wikipedia definition, which is a much more technical definition once you get going than we're going to go, but this comes from a study of something called thermodynamics, which really is what this unit is about. What's thermo mean? Heat. What's dynamics mean? Movement. So when we talk about thermodynamics, we're studying the movement of energy in the universe, or the movement of energy throughout systems. Does that make sense? And in thermodynamics, for any given system, quote unquote, enthalpy is the total internal energy in that system. Total internal energy in that system. What's that mean? Huh? Yeah.
Is it like the energy or like heat energy it produces?
Not that it produces. In fact, if it produces energy, then its enthalpy is changing, and we're going to get to that. It's not the energy that it is producing, it's the energy that it contains. It's how much energy is currently in the system. All the energy that is currently in a system, that is that system's enthalpy. So for example, you could talk about a single molecule as a system, one single molecule, say a real simple one. Say we had water. You don't have to write this. Don't write this yet. What energy is inside that molecule right now? Sorry? Okay, so its mass is a form of energy. So it contains all of its, we know from Einstein's E equals mc squared, right? Mass is a function of energy. So all of its mass is some of its energy. That's part of its enthalpy. Good. What else? Yeah, all of the energy of its electrons in orbit, including the bonds. All of that energy is inside of that molecule right now. That is part of its enthalpy. What else? Particle theory of matter tells us that particles are doing what all the time? Vibrating, moving, either if it's a gas moving freely or if it's a solid or a liquid oscillating in place. All of that energy inside the molecule is all part of its enthalpy. So enthalpy is the internal energy of a system. If we consider, probably, if we consider a single molecule, it includes, its mass, its bonds, heat energy, pressure, etc. So it's all of the energy inside of a system. Does that make sense? This is challenging to measure because, as you can imagine, it involves a lot of different things. Does that make sense? So we're not actually going to measure the enthalpy of any molecule in this course because all of these things to consider is a lot of stuff. Does that make sense? But what we will measure is a change in energy. We can measure changes in enthalpy. So enthalpy is denoted with the letter H. H is how we measure enthalpy. And since it's a unit of energy, we would use either joules or kilojoules to measure it. Changes in enthalpy would therefore be denoted as what? If H is enthalpy, a change in enthalpy would be denoted as delta H, delta enthalpy. Very good. So delta H is measured in, for what? Just put them in the back for now, then that's okay. Thank you so much. I know, I love it. I'm going to throw them out today, but first I'm going to look at some of those under the microscope. So delta H would be the change in enthalpy. Does that feel okay? So now, what that means is, let's look at an example here of burning hydrogen to make water. All right? Can we look at that example here? For example, hydrogen gas, a mole of hydrogen gas can react with half a mole of oxygen gas to make a mole of water. But when we do that, this reaction releases energy. It releases energy. What's our word for that? Exothermic. Okay, so this reaction releases energy. In other words, we say that it is exo, outside thermic, heat energy. It releases energy. Now listen, if it releases energy, then that must mean that whatever this amount of enthalpy was, however much enthalpy was stored inside of the hydrogen and the oxygen, if we compare that to the enthalpy stored in the water, what must be true? Sorry? Yeah, these are different from each other. How much different are they? First of all, which one has more energy? Which one has more energy stored in it? Hydrogen and oxygen separately, or water once they get put together? Which one has more energy inside of it? When they're separate. When they come together, they release energy. And if they're releasing energy, that energy had to come from somewhere. It came from inside the molecules themselves. Does that make sense? So, this is our note here. In the above reaction, the total energy, the total internal energy, I am down a note, and I'm sorry about that. You're going to have to, I don't know why they didn't all print. I printed the same number I always print. So you might just have to follow along. I'll go get a copy, but I don't want to run out of time. Yeah, it should be in. It's actually up here. It's right there. Somewhere. It's right there. That's wrong class. That one. Right there. Yeah. Do you mind putting the rest in the handout folder? So in the above reaction, the total internal energy of H2 and O2 is higher, which we're going to call enthalpy 1, is higher than that of H2O. We'll call that H2. How much higher? Well, we know exactly how much higher it is because how much energy got released? Yeah. The 242.0 kilojoules of energy released is the difference in their internal energies. In other words, we don't know how big H2 is, and we don't know how big H1 is, but we know that the difference between them must be how much? 242.0. Now, when we go to write this then, we could say delta H equals H2 minus H1, right? Does that make sense? That's always how we do a delta, right? The final minus the initial. Bless you. But when we do that, which one of these has to be the lower number? H2 or H1? H2. We know that's the lower number, right? Which means that when we do that math, the difference is going to be 242.0. But if H2 is the smaller number, when we do a smaller number minus a bigger number, what do we end up with? A negative number. And I want to mention this. So the delta H in this case ends up being negative. And we can say it's negative 242.0 kilojoules per mole. Because for every mole of hydrogen that we burn, that's how many kilojoules we get. If we burned 2 moles of hydrogen, how much energy would we expect to release? 484. If we burned 1,000 moles of hydrogen, we would release 242,000 kilojoules of energy. This makes sense, right? You instinctively understand that 1 log has a certain amount of heat it can give off. So if you want to build a really hot fire, you're not going to put 1 log on it. You'll try to put a bunch of logs on it, right? You understand that a certain amount of gas can produce a certain amount of heat. So if you want to heat something up on the stove, you'll give it lots of gas if you want to heat it up quickly. And if you want to heat it up slowly, you'd only give it a little bit of gas. We instinctively understand that the amount of heat that gets released depends on the amount of stuff you react, right? Does that feel intuitive? That's what this is saying, is that if we look at this reaction, every time we burn a mole of hydrogen, we release 242.0 kilojoules of energy. Now, noteworthily, we're going to mention the unit, or not the unit, the direction here. Exothermic reactions have negative delta H values. And that's because delta H doesn't measure how much energy is in the environment. It measures how much energy is in the actual chemicals that you're working with. Look at me, I want to make sure this is clear because this is so important. And if you get this, it'll make your life way easier. And if you miss this, you'll confuse it a bunch. So again, when we talk about H or delta H, we're talking about how much energy is in the chemicals, not in the surroundings, in the chemicals. If the surroundings are getting hotter, then that means energy is going into the surroundings. But if energy is going into the surroundings, making it hotter, then the chemicals themselves must be losing that energy, which means that their enthalpy is going down. They're losing energy. So if the surroundings are getting hotter, you instinctively might think, oh, that'd be a positive delta H because that's energy being released. But again, the things that are actually doing the reacting then must be losing that energy. So anytime the surroundings get hotter, the delta H is negative. If the surroundings get cooler, then the delta H must be positive because that actually means they're sucking energy in from the environment to make the reaction happen. Does that feel okay? Does that make sense? It's a key concept. Exothermic reactions have negative delta H's. We're going to mention this like 5 times so we don't forget it. And endothermic reactions, reactions that absorb energy, have positive delta H's.
Does that actually happen? Like,
This is what actually happened.
like you're saying if stuff can also like absorb energy, so like the temperature gets like cooler around.
Oh yeah. Have you ever?
water.
Is there any athletes in here who've ever gotten the cool packs that like just do their thing and then when you snap them they get cold, like those cold packs? That's a chemical reaction. So all that happens in those is there's a little balloon inside that contains one chemical surrounded by a bunch of surrounding chemicals. And it's designed so that when you give it that little snap, the 2 chemicals mix and the reaction happens. And it's an endothermic reaction, so it sucks in heat and it cools everything down. But there's all kinds of chemical reactions that absorb energy.
So like the actual thing doesn't get hotter.
What do you mean?
Because like you were saying with like the other reaction, if the heat is going like outwards, then that means the thing is losing like energy.
Yeah, that's right. And we're not talking about losing heat energy. In fact, the thing might gain some heat energy because it's going to heat up like everything else heats up, right? But what it's losing is the energy that it takes to form bonds Every time you make and break bonds, you absorb and release energy. Does that make sense? And so if you break a bunch of bonds and make a bunch of new bonds, if the new bonds you've made, if all of that system requires more energy than what you started with, that energy has to come from somewhere. And it's going to come from the surroundings, and you're going to get a temperature decrease around it unless you provide some other form of energy. By the way, this is not limited to it. Boiling water absorbs heat energy. We don't think about that making the surroundings cooling because it happens while things are hot, but it actually is cooling down the surroundings. It's just that it's cooling down something that is hundreds of degrees to just being about 100 degrees. Does that make sense? In other words, a gas flame should heat everything around it up to pretty quickly hundreds of degrees. But if you put water there, it doesn't heat up to hundreds of degrees. Instead, it heats up slowly, and boils off into a gas nowhere near the hundreds of degrees that flame wants to be, because boiling water is an endothermic reaction. It has to absorb a bunch of heat energy. The flip point to that is steam turning back into water is exothermic. It releases heat, which means if steam hits you, you get horrible burns. Steam burns are horrifying because the steam hits you, the steam is hot, and so you absorb all that energy. And then as the steam condenses back into water, all the energy it absorbed to boil has to go somewhere and it comes back out. And so when steam condenses back into water, it releases huge amounts of heat energy, which then burn you further. So that's why if you ever work in a system that has steam in it, like with this is why gas fitters have to have very serious safety training. But even in a restaurant, I used to work at a restaurant that has steam systems throughout the whole restaurant. We had steamers around, and we had to have safety training on that every year, because if boiling water is endothermic, if it absorbs energy, then that means condensing steam back into water must be highly exothermic. You get the energy back, and you do, so steam is dangerous. Does that make sense? Yeah. Cool. That was a good question, by the way. So endothermic reactions have positive delta H's. My deltas aren't looking very delta-y today. That's better. And actually, the next example we have here is precisely what you were just asking about. For example, consider the vaporization of water, which is a fancy way of saying turning liquid water into a gas. Which could be boiling, but it could also just be, what's the other way that happens? If I leave this cup sitting here, I mean, this one has coffee in it, so other weird, gross things will happen. But if I leave a cup of water out, what happens over time? It evaporates. It actually takes just as much energy to evaporate water as to boil it. It just happens slowly instead of quickly, right? The energy is still the same, which is, somebody tell me in words what this means. Or if you prefer to look at the equation itself, what is it saying? It's saying that if you have a mole of water and you want to turn it into a liquid water and you want to turn it into a mole of water vapor, what do you have to do? You have to give it energy. How much energy? 40.8 kilojoules, which is a not insubstantial amount of water. You know this. If you want to, I'm a tea drinker. I love drinking tea. And you know that it takes a lot of energy just to heat the water up, right? But have you ever left the water boiling too long, you forgot about it, and it just keeps boiling? It takes a long time to boil all the water off, because even once it's up to 100 degrees, it still doesn't just automatically boil. If you heat water to 100 and then turn the heat off, it's going to stop boiling, right? Because it's not enough to get water to 100. You have to get the water to 100 degrees, and then to turn it into steam, every mole of water requires 40.8 kilojoules of energy, which is like, do you guys know how much energy that is? Like, just to give you a sense. How big is a big burner on a stove? How many watts is the large burner on a stove? So the large burner on a stove typically uses 3,000 watts. Does that make sense? So we'll go with that number. Just, does anyone know what a watt is? Back to your grade 9 science. Large burner, it's a rate. A watt is, so the large burner, we'll call it 3,000 watts if you put it on full. A watt is the same as saying 3,000 joules for every second. Does that make sense? Which is, if we convert that to kilojoules, how much? 3 kilojoules per second. So just to give you a sense, if you got your burner going as hot as it can go, all right? Your burner is on full, and you put your hand on it, you are getting 3 kilojoules for every second you keep your hand on it. Does that make sense? Can you picture that? Now, would you want to keep your hand on there for a second?
Yeah.
Presumably no, because that's a lot of heat, right? In fact, just a brief contact with it would cause you serious damage. 3 kilojoules is that's how much energy that is. Does that make sense? It's how much energy your large burner can put out in a second. Okay, now, with that in mind, that means once the water is already at 100 degrees Celsius, it would take about 13 seconds to boil a mole of water. And of course, a mole of water isn't much water at all. How much is a mole of water? Oxygen weighs 16 grams per mole. Hydrogen weighs 1 gram per mole. So 18 grams. So that means, which is 18 grams of water, thanks to its nice, easy conversion, is 18 milliliters of water. Not a lot of water. That means it takes your stove, if it's being perfectly efficient, about 13 seconds to boil 18 mils of water that is already at the boiling temperature. Does that make sense? So if you had a pot of a liter of water, or 1,000 grams of water, you could do the math and you could figure out how many seconds it would take your burner to boil all that water off, even if it was already to 100 degrees Celsius. And of course, we learned yesterday, you could figure out the math first of how long it would take to get up to 100 degrees, because we know the specific heat capacity of water. We know that it takes 4.2 kilojoules to increase the temperature of water, 1 gram of water by 1 degree Celsius, right?
What was the number of liters you were saying? 1,000 liters?
1,000 milliliters would be 1 liter, right? Anyway, so if you wanted to boil a liter of water, would that be a good test question? You have a liter of water on the stove, it's at 20 degrees Celsius. How much energy to bring it up to 100? How much energy to boil it? Probably. Is that probably a question just like that on your test? Probably. I haven't made it yet, but that's a good physics question, right? I know this isn't a physics class, but we should be able to do that, right? Like, that's pretty trivial stuff. So if we look here, what this is saying, this equation says that 1 mole of water requires 40.8 kilojoules of energy to vaporize. Is this reaction exothermic or endothermic? This is endothermic. Does it have a positive or a negative delta H? Positive delta H. It has a positive delta H because it is absorbing energy. So the energy inside the material is going up. In other words, it takes more energy for water molecules to be in a gaseous state, to be away from each other, than it takes for them to be in a liquid state, which is more still than for them to be in a solid state. So they have to have a higher internal energy to be gaseous than they do to be liquid. Yeah?
What is the delta H vapor mean?
That is the change in enthalpy required to vaporize. That's a great question. We will often write a little subscript just so you know what delta H we're talking about. because water can have a bunch of delta H's associated with it. There's the delta H of making it by burning hydrogen, but there's also the delta H of freezing it. There's the delta H of boiling it. There's the delta H of melt. Do you just see what I'm saying?
Yeah.
So we often will use a little subscript down here so you know which one we're talking about. Did that answer your question? That was a good question.
So that just means how much like
The change in enthalpy required to vaporize it. Yep, exactly right. Yeah.
If the delta H for converting, like making water, was negative, why is it not negative?
Ah, good question. Because it has to do, just like in algebra, with what side of the equal sign it's on. So if you think about it, the energy is on the side of the products, which means the energy is on the release side. So if you wanted to put the energy on the side of the initial system and bring it over here, it would be negative. So algebraically, by putting it over here, it becomes a positive number. But if we do the delta, because remember, delta means, because the actual H value is some enormous number, right? And the actual H value would be like saying, we start off with, I'm just going to make it easy, 200,242 kilojoules. It would actually be much bigger than that. And we end up with 200,000 in the system and 242 released. Does that make sense? And so the delta H is what you get when you subtract these two together. That's where the actual number comes from. Does that answer your question? And we're never going to write it that way, in part because we don't know the H values. We calculate delta H, but we don't actually go back and try to calculate the full enthalpy values, because that just contains so much stuff. We'd have to calculate the mass energy equals mc squared. We'd have to calculate the bond energies. We'd have to calculate its kinetic motion. There's way too many pressure, all these things. So we don't measure H directly, but we measure its change. Sorry, can I do it one more time? Okay, I'm done.
is this like a revenge to the construction workers?
They're not hearing that. I just found it charming that it does that. I don't know why it does that. Anyway, how's that feel? Does that feel okay? Not too bad? Again, what we're actually tracking here is the energy inside the compounds. Now, this assumes a perfect world, by the way, that when they release energy, they don't then reabsorb any of it to increase their temperature. In the real world, they're going to get some of that back just by heating up. That's okay. Nothing is a perfect transfer. But in theory, if they didn't reabsorb any of the energy they release, it'll release. In this case, this reaction will release a full 242 kilojoules for every mole. But this reaction here isn't releasing energy. It has to be absorbing it. And we can tell that, if we want, by looking at the reaction and saying, which side do they write the energy on? But more often than not, we're not going to write the energy in a reaction. You've never seen the energy written in a reaction before, right? Usually we don't include that. Usually we write the reaction without the energy in it, and then we just list its delta H value, and you then have to know that a positive delta H means that it's absorbing energy, and a negative delta H means that it is releasing energy. Good. Does that feel okay? All right. Let's take a look at the next page then. Here are some reactions that just tell us the molar enthalpies of fusion and vaporization. What does fusion mean? In a fusion reaction, it means that we are going from being X as a liquid to X as a solid. Does that make sense? That's what fusion is. What is vaporization? That would be X as a liquid going to X as a gas. Now, we don't need to give the other ones. We don't need to also give the delta H of melting, because the delta H of melting will just be the delta H of fusion, but backwards. Whatever energy you had to put in or take out to make it fuse, that's what you're going to have to put back in to melt it. Does that make sense? Likewise, we don't need to give the delta H of going from gas to liquid because it'll just be the same as liquid to gas, but it will be reversed. Does that make sense? Look at me. I promise it makes sense, and you do instinctively get it. Let's take the example we have above. It takes 40.8 kilojoules of energy to take liquid water and turn it into a gas, which means you can tell me how much energy I'm going to get back if I take a mole of gaseous water and turn it back into a liquid. How much energy would we get back? Yeah, that one would be negative, which would mean it would release energy, but it's going to be 40.8. Does that make sense? There's no point listing both of those because they're just opposite of each other. So if you know how much energy it takes to melt something, then you also know how much energy gets released when you freeze something. If you know how much energy it takes to boil something, then you know how much energy you get when you condense it back to a liquid. Do I have to say that again, or did that feel okay? For those reversible reactions, there's no point having a table with both the numbers, because what you would have is a table of a whole bunch of numbers, and then the next column would be all the exact same numbers, just with the opposite sign. That's a waste of paper and space. Does that make sense? You could do it, nothing wrong with it. But if boiling and condensing are exactly opposite of each other, then there's no reason to list them both. You just understand that if you know one, you know the other. And if freezing and melting are exactly opposite of one another, which they are, there's no point in listing both. If you know one, you know the other. Comfy? All right. So let's take a look. What does it take more energy to melt? Sodium or sodium chloride? Sodium chloride. Which means if I had both of these materials at their melting point, whatever that might be, it's going to take a lot more energy, about 10 times more energy, to melt the sodium chloride than it would take to melt the sodium. Which makes sense. Sodium is a metal. Metals melt relatively easily, right? Sodium chloride is a big dumb rock, and rocks do melt, but they melt less easily. Yep, so again, remember, that means the number to go from solid to liquid is the exact same. It's just instead of releasing it, it's being absorbed. If you know one, then you know the other. So it's weird to think, but the heat of fusion, or the enthalpy of fusion, is also the enthalpy of melting. So weirdly, when you talk about something's melting point, a chemist is going to go look up its heat of fusion, which feels backwards, but it's just the same number in reverse. Does that make sense? You're right to be a little bit like, well, that's weird, because it is weird, but if you step back and look at it, you go, right, it's going to be the number in the wrong direction, but it's going to be the right number. Okay, so let's do some math with this. Ready? Ready for math?
Yeah.
Woo! All right, let's go. Let's go, team. We're going to do some dimensional analysis, because we know Freon 12, which has a molar mass of 120.91 grams per mole, is a common refrigerant that is vaporized in tubes inside an old refrigerator. We no longer use Freon 12, but because it's bad for the environment. But here it is. So what it does, very cleverly, all your fridge does is it pumps a bunch of fluid inside your fridge, and then it takes that from a narrow little tube into a big wide tube. That's all it does. All your fridge does, it takes a bunch of narrow tubes of Freon and it puts them into the inside of your fridge, where those collect into a bigger tube like this. And as the big tube gets bigger, the pressure drops. And as the pressure drops, this is going to become a gas, right? But if it becomes a gas, it has to absorb a bunch of energy, because it takes energy to go from being a liquid to being a gas. So in the fridge, when this tube opens up and the pressure drops, it's going to have to absorb energy. And so what happens to the things inside the fridge then? Well, they have to give heat energy to that gas to turn into that liquid to turn into a gas, which means everything in the fridge gets colder. Then we pump it back outside of the fridge. We actually just let it flow. It doesn't even need a pump. It goes back outside the fridge. Fluids flow. Where we do pump it back into little narrow tube, which means it's going to have to turn back into a liquid. But to do that, it's going to have to let all that energy out, which it does outside of the fridge, and we blow a little fan against it to make that energy go away, at which point we let it circulate back into the fridge, where it goes into a wider tube, where it does what to all the surroundings? It has to absorb energy because it's going to turn into a gas. And you can't escape the molar enthalpy of vaporization. To take a liquid and turn it into a gas, you have to absorb that energy. So that's all your fridge is. It's just a wide tube on the outside, a narrow tube on the inside, and you keep shuffling back and forth between the two. You put a fan on both so that inside the fridge, as it goes into the narrow tube and turns it goes into the wide tube and turns into a gas, it's going to absorb a bunch of heat. And when it goes back outside and back into the narrow tube, it's going to release that heat, and you just cycle it through with a pump. That's it. That's all a fridge is. That's all an air conditioner is. That's all any of these devices are. Pretty clever, right? And we pick a thing that, as it happens, releases and absorbs a lot of energy. Look how much energy it takes to do this with Freon 12. We could do it with water, but the problem is to do it with water, that happens way up at 100 degrees Celsius. So you could run a wonderful refrigerator using water as long as the temperature you wanted to keep everything at was around about 100 degrees Celsius. Is that going to work well for us? No. So instead, we use Freon 12, which gives us just as much, almost as much energy, but it works nicely at the temperatures we're working at. Does that make sense? You could also use just methanol. You could also use ethylene glycol, which is even better. Big industrial freezers use ethylene glycol. If you go to a winery, you'll see that they have like cooling jackets that go around these big industrial chemical vats. They use ethylene glycol because it gives you even more energy. Does that make sense? Anyway, so what we're given here then is we have Freon 12, which I'm just going to say Freon in its liquid state goes to Freon in its gaseous state. And when it does that, it has to absorb energy. How much energy? We said on the previous page, the delta H is what? 39.2 kilojoules for every mole, which means, and it's positive, which means it absorbs. How much? I don't know. What is it? Cool. 99, 2 decimals. Very specific. So it absorbs this energy. How do we know it absorbs the energy? The delta H is positive. Good. Okay. This is our reaction. All right? Now, the question is, if you have half a kilogram of Freon in your fridge, how much energy can it absorb per cycle? Well, let's do a little bit of math. We have 500 grams of Freon. And this is where we want to do dimensional analysis. I want to know from how many grams of Freon I have, I want to know how many kilojoules of energy will be absorbed. Can I go directly from grams of something to how many kilojoules of energy it can? Well, this doesn't tell you how many kilojoules get released per gram. It tells you how many kilojoules get released per mole. So first we're going to have to convert grams of Freon to moles of Freon. And then after we've done that, then we can convert moles of Freon to kilojoules of energy because we know the delta H. The delta H tells you how many kilojoules get released or absorbed for every mole. How do we go from grams of something to moles of something else? We need to know the molar mass, and where do we find that? On the periodic table. Now, do we have to work this one out ourselves? No, in fact, the question gives us the molar mass for this one. Isn't that nice? And where did we get the delta H? You either have to find this experimentally or you have to look it up. And in this case, we looked it up and we found it to be 34.99 kilojoules per mole. Yeah?
What is that thing beside absorb this?
E. That's an E. I'll just write the word energy. Sorry. So this is going to be our dimensional analysis. Start with grams. We don't want to talk about grams. We want to talk about moles. Then we'll say we don't want to talk about moles. We want to talk about kilojoules of energy. So if I don't want to talk about grams, where do I put it in the next fraction?
Bottom.
On the bottom. What do I want to talk about at this stage? Moles of freon. Do we have a number for that? Do we know how many moles are in a gram or how many grams are in a mole of freon?
Yes.
Okay, what is it? 1 mole has 120.91 grams. Good. What units cancel at this point? If I were to stop calculating now, what would I know? I would know moles is how many moles of freon there are. Good. But that's not enough information because I want to know how much heat they're going to absorb. So what don't I want to talk about? Of? Where do I put that? What do I want to talk about? Kilojoules of energy released, right? Good. Do we have a number for that? Which is? Is it true that 1 kilojoule releases 34.99 moles? Do we like that? No. What we're saying is that if we have 1 mole of freon, it will release 34.99 kilojoules. And that would be the obvious mistake to make. Don't feel bad if you made it, but I always find that saying it aloud helps, right? If you talk your way through it, it's going to help you avoid mistakes. If you need help with your dimensional analysis skills, if you have forgotten or if I didn't teach you, I will put those notes back up in this section so you can look them up. I'd be happy to print a practice for you, but then we can do the math. 500 times 1 divided by 120.91. That's going to be what? A little bit more than 4. That's going to be 4.3-ish. And then 4.3 times 34.99. That's going to be, we're going to be sitting around 160, give or take. What do we get? Cool. 144.69. All right. And how many sig figs do we have here? We're going to assume that this is 500 grams exact, like to the nearest gram. So we have 3, so our answer should be 145 kilojoules of energy. Which, if you think about it, that means by the time all of the freon is cycled through your fridge, which takes some time, it will absorb as much energy as your stove going full blast for quite some time, right? That freon's absorbing a lot of energy. Now, it's not 100% efficient at all. It's nowhere near 100% efficient, though air conditioners and fridges and freezers have gotten a lot better, have gotten a lot more efficient. But this is actually pretty incredible stuff, right? This is why you can be comfortable indoors in the summer. This is why this is why the global population, or not the global population, but say like the American South, their population always lagged tremendously behind the population in the North because, boy, they had hot summers. And with the advent of air conditioning, people started moving south voluntarily, like recreationally, right? That is a post-air conditioning development, right? But this technology works. Yeah. When you change the setting, it's just controlling what percentage of the time the thing's actually working. It doesn't actually change. Some more sophisticated air conditioners will have multi-stage pumps, where if the temperature is close to what you have it set to, it'll run with the pump running fairly slowly. And then if the difference between what you want it to be and what is now is big, it'll run it faster. But most air conditioners just are either on or off, and all your temperature setting is doing is controlling what percentage of the time it's actually on. So most of like a good chunk of the time your fridge is running, it's just circulating air, and you'll hear it. Modern fridges aren't as loud. Older ones, you'd really hear it kick in, where all of a sudden in the next room you'll hear the fridge go like from mode 1 to mode 2, where it's humming a little bit to humming a lot louder. That's when the compressor is kicking in, and it's actually actively doing this. Have you experienced? Do you know what I'm talking about? Like, have you heard that before? Yeah. So all your thermostat is doing is controlling, for the most part, how often the fridge is on compared to how often it's not on. In theory, If you leave your fridge on all the time, it will have a maximum amount of heat it could possibly absorb. That's going to be more than you need. It would freeze all your stuff. But there will be a limit of how much heat energy it can absorb. And it'll reach an equilibrium state, which will be a set temperature. Yeah.
Is that what freezers do?
No, because I mean, that's energy inefficient too. Freezers run a bit more. But the other thing freezers do, smart ones, especially the old ones that you lift up, they're incredibly efficient because cold air is dense, so it stays low. So a freezer is able to barely ever run, which is also why the more convenient freezers that open like fridges, like that have the door, way less efficient. A drawer-style freezer is great because all that cold air you've spent money to create wants to stay where it is. Whereas when you open a freezer that's sort of cupboard style, now that cold air is able to fall out into the room. So an old-fashioned chest freezer, the one that like your grandma probably has, that like you lift up, barely has to run at all because it's just a big thermos. It's just really, really energetically efficient. So it does not take a lot of energy to run a chest furnace as long as you keep it shut.
Yeah, I see that with like fridge, because like some fridges, like they have the freezers on the top, and then when you open it, like you can see the air.
Exactly, and you're losing all of that. So the bottom mount freezer is a lot more efficient for keeping the freezer frozen. Now, those old fridges used less energy on fans because the theory there was keep the coldest air here, and then naturally in the fridge, that cold air is going to make its way down. So there's a trade-off in these things. But yeah, the modern drawer-style freezers are actually much more efficient for energy than the old-style open up as a door on top. Where, yeah, like you say, you can see the cold air go whoosh, and it's like you've paid for all that cold air. When my grandfather taught me to drive, he was an accountant. He was a real cheapskate. But he was like, don't use the brakes. Every time you use the brakes, you're wasting money. Like which is true. Learn how to coast. Learn how to anticipate what the driver in front of you is doing and coast. Because every time you've spent perfectly good money to accelerate, and now you're spending more money on the form of brake pads to slow down, you're just spending money twice to accomplish nothing. Cars do this themselves now. Way back in the 90s, my grandfather, every time he came to a red light, would turn his car off. Then when it turned green, he would turn his car back on and go. He also had a habit of, if you were going downhill for a while, when he was teaching me to drive, I'll never forget the first time he did this. We were going down a pretty big hill out in Pelham. He just reached over and turned the car off. And I was like, what are you doing? Like, now I don't have power steering. I don't have power brakes. He's like, you're fine. Steer the car. He grew up in the Great Depression. He knew what it was like to have no money for food, and he was not into wasting money. Thank you very much. Something we probably something to consider. Not a guy who would, for example, skip the dishes to get lunch, shall we say. Knew the value of $1. Anyway. Yeah.
Changing liquid into gas, it would absorb energy, and from gas into liquid, it would release energy.
Yep, exactly right. Sorry, I just had to make sure I was hearing what you said. Yeah, exactly right. Yeah, and the one is really intuitive. We know that you have to pump energy into a liquid to make it a gas. That one makes sense. It is a little weird to think that when that gas turns back into a liquid, it's releasing a bunch of heat energy, but the math tells us that's what happens. And if you've ever had a steam burn, and I had a steam pipe burst on me once at a restaurant where I was working on something, and I got a good chunk of it in the shoulder. And oh my God, let me tell you, you feel it. So the math tells us that energy gets released, and my incredibly hot shoulder that day told me that all that energy does get released. So it's part of the danger of steam.
At least look cool.
Sorry?
Did it at least look cool and make you look tough?
I mean, I look cool all the time, right? What kind of question is that? So therefore, it takes 145 kilojoules of absorbed energy. What?
What is that? 5.
Let's carry on.
That 8.
That looks like R.
Okay, there we go.
You can't.
Where was I? Nobody likes any of you. It takes 145 kilojoules of absorbed energy to vaporize 500 grams of Freon. And again, guys, that is assuming that it is already at temperature, the appropriate temperature. Does that make sense? That doesn't count what you would need to do to get it to its proper temperature first if what you were trying to do is boil it. This assumes you're already at the proper boiling point. It's just the act of actually vaporizing that requires absorbed energy. And again, what you would experience with this, you have experienced this before. Does anyone ever felt like a spray can while you're spraying it? And what happens to the nozzle of any spray can when you're spraying a liquid out of it? Whether you have it gets cold. Why does it get cold? Because if you shake it around and you hear that it's a liquid in the can, right? But then when you spray it, it's becoming a gas, it's vaporizing. It has to absorb energy to go from liquid to gas. It just has to. There's nothing you can do about it. And to do so, it has to get the energy somewhere it's going to get from the surroundings. You're going to feel it getting cold. Does that make sense? This has nothing to do with changing its temperature per se. It's that for something to go from being a solid to being a liquid, or to go from liquid to being a gas, it has to absorb energy. Yeah.
Then if it's absorbing energy, why does it get cold?
Because it's absorbing energy. So what is coldness? Coldness isn't the energy inside the molecule. It's the energy of the surroundings, right? It's the average kinetic energy of everything it's surrounding, stuff bumping into each other. So if there's more energy inside the molecule, where did it get it? From all the bouncy around going on around it. So if it absorbed all that bouncy around energy to turn into bonds, there's less bouncing around happening all around it, and we experience that as a lower temperature. Does that make sense? It's weird. You got to wrap your head around it. Yes, the temperature is a part of that thing's internal energy. So you're right. As it's absorbing energy, it's cooling down. Its kinetic energy is actually dropping. But that's okay, because it's not the kinetic energy that it needs to absorb. It needs to absorb it to change its bond energy. In fact, you know what kind of bond energy is changing. The intermolecular bonds, the bonds between molecules, is going from being a relatively strong hydrogen bond that's holding something together as a liquid to now the much weaker forces of something being a gas, each individually separated. And to break all those bonds requires energy. Does that make sense? All right. So I want you guys to try this one. Calculate the enthalpy change of vaporizing 150 grams of water at 100 degrees Celsius. And then we're going to do in the lab tomorrow, the last little bit, we're going to learn about calorimetry. We're going to attempt to learn about calorimetry. We're going to use, no, this one you're doing.
You said I already finished that.
Aren't you fan? I mean, you can do it now if you want, but we're going to physically do it tomorrow.
You said change. The change of age is given, or in the lab. Then how are we going to find it?
You can't find H, but you can find delta H. We talked about that already. All we need to do is assume that all of the heat change is going into the surroundings, right? So in other words, if it's exothermic, we're going to assume that all the energy that gets released is going to get absorbed by the surrounding water and its temperature will go up. Or if it's endothermic, we're going to assume that all the energy that goes into it came from the surrounding water and we can watch its temperature drop. And then we know by Q equals mc delta T that we can determine what that change in energy is. So Q, the change in temperature of the water, should be just the opposite of delta H. If the temperature of the water is going up, then the delta H will be negative. It'll be the same number though, right? If the water has absorbed 1,000 joules of energy, then the chemicals that reacted must have released 1,000 joules of energy. And if the water has lost 1,000 joules of energy, it must have gone into the chemicals. So you got to think like an accountant, because this is how your bank accounts work. Anytime you have a positive transaction in your bank account, somewhere else out in the universe, somebody has a bank account of the exact same number, but it is negative. In other words, if I send you $1,000, your bank account must go up by $1,000. Well, mine must go down by 1,000. It has to balance out, right? So like when you go to the store and there's an interact charge on your thing because you tap your card, your bank account goes down by $3.52 or whatever. The bank account of that institution goes up by that much. It all balances out, right? So when something moves from one place to another, there must be a negative value here that must be balanced by a positive value somewhere else. So if Q is the amount of energy in the surroundings and delta H is the amount of energy in the system, those will always be equal but opposite, right? Delta Q, the change in heat, the change in thermal energy in the surrounding system, if it goes up, then the enthalpy of the reaction system must have gone down. And if this goes down, if it cools down, then the energy in the reaction system itself must have gone up. But temperature is only a piece of this. Temperature is all of Q. Q is just a function of temperature, right? It's just saying what is the heat of the temperature of the system, of the whole surrounding system, whereas the temperature of this thing may go down. But that doesn't mean its overall energy has gone down, because temperature, if a chemical reaction happened, isn't the only thing. Yes, that's a part of it, but there's also its bond energies. And that's what's changing in a chemical reaction, is the bond energies, right? When we do a chemical reaction, it's not changing temperature because we heat it up with a candle. That might be necessary to make a reaction happen. But in the end, it's releasing energy because the bonds are breaking, right? We'll get there. We're not there yet. Quiet you. Mm-hmm.
It's going to be the same on sides because water exchanges.
And then if you, that's exactly right. Then if you went over here and did Q equals MC delta T, you would find that that exact same amount of heat will perfectly describe the temperature change for the amount of water you worked with. It should all balance out perfectly. Now, in real life, does it balance out perfectly? No, because you're always going to have some energy escape to the environment because we don't account for the fact that the chemicals themselves also change temperature, which is a bit of absorption. So in real life, your number should be very close to perfect, but it will never be exactly perfect because you can't account for all those variables perfectly. But these are good questions. Are my answers helping at all? Maybe doing it will help. Maybe doing it will help. Let's try this one together before we have to go. We have grams of water, right? And we're going to turn that into grams of steam, right? Because that's what we're doing here. But we don't care about that. But what we're saying is H2O as a liquid is going to turn to H2O as a gas. When that happens, is this going to absorb energy or release energy? Absorb energy. How much? Help me out. 4.8? 40.8? 40.8 what? Per? The minute strong.
Our salad is Caesar salad for $4. Entrees are chicken penne, Alfredo with garlic bread for $6. Pizza for $2. Chicken pizza for $3. And remember, deals, we always have French fries. Small beef for $15. $4. We also have coconut macaroon cookies for $1 each. Make it a good day, Eagles.
So we want to go from how many grams of water we're working with to how much energy is going to have to be absorbed. But can we go from grams to kilojoules directly? So we have to convert grams to moles. And once we know how many moles of water we have, then we should be able to tell how many kilojoules of energy get absorbed, because we know that every mole of water absorbs 40.8 kilojoules of energy as it goes from being liquid water to steam, assuming it's already at the boiling point of water, which in this case it is, right? So we can start off with how much water? 150.0 grams of water. And we're going to say, that's a weird place to put the O. We're going to do what? What do I do here? What don't I want to talk about? What do I want to talk about? So where do I put it? On the bottom. And we want moles of water. We'll put that on top. How many grams are in a mole, or how many moles are in a gram of water?
18 grams.
Yeah, we could say the molar mass of water is 15.9994 grams per mole plus 2 times 1.079. 0079, sorry. Has anyone done that? What do we get to a little bit more sophistication here? Because we got 4 sig figs to work with, so I want 4 sig figs in this. What do we got? 18 point what? 18.00. 014. Awesome. 148. Okay. So we know those 18.0148 grams in every mole of water. If I stopped calculating now, what would I know? I'd know how many moles of water I have. Is that what I want?
No.
Where do I put that? On the bottom. What do I want to know? How many kilojoules of energy will be released, right? And what do I know? every 1 mole releases 40.8 kilojoules. And this should be somewhat trivial. That should be a little less than 10. That should be 8-ish, 8 times 4. This should be on the order of 320, 330. What are we getting?
Not 320 exactly, but I did just 18.
Yeah, if you did just 18, you'd get 320 exactly.
339.7.
339.7? Great. And what will the unit be? Kilojoules. And how many sig figs should I actually have? What's limiting here? Yeah, this is 3 sig figs. So my answer should be 340 kilojoules of energy. Therefore, 340 kilojoules of energy are required to vaporize 150.0 grams of water. How's that feel? Not too bad? All right. You can start the homework if you want, but the last piece of this we're actually going to go in the lab and attempt to do tomorrow, and hopefully seeing it done actually, like in person. Hello, how are you? Nice to see you. Welcome.
And there was some interesting. You gotta give me like 2,000. It was interesting.
Sam, don't stand for that.
Yeah, I'm setting my